So I'll quickly go through maybe the syllabus, so then we can talk about the different aspects that things we're going to be studying this semester. So power electronics is the study of electronic circuits that are used to convert power, right? So if you look at everything around you, so example, this laptop here is a battery-powered laptop, correct? You charge it from the mains, right? You plug it into the mains, and there's a box between you and the mains, right? And that's power electronics, right? So that's something that a power electronics person would sit and design. Your cell phones, same thing, right? Your cell phones are running off a lithium battery that's probably 3.7 volts. This 3.7 volts is something you're charging sometimes from your USB. Your USB is about a 5 volt DC output, right? So in that case, you are taking 5 volt DC, converting it to what? 3.7 volts or so DC to charge the battery, right? So for you to charge the cell phone's battery, you have to sort of push current into the battery. The way you push current from point to point is typically what? If you have 2 points, how do you push current from this node to this node? There has to be a voltage difference, right? If there's a voltage difference and then there's an impedance, then you're able to push current. So you're able to push current from a point of higher potential to a point of a little lower potential, right? So you typically control the value of current going into a battery because batteries don't like to be misused. They don't like to be charged too fast, and they don't like to be charged too slow, and they don't like to be loaded, for example, using peaky currents. For example, you're drawing peaks of current from them at a high frequency. They don't like all of that kind of stuff. So because batteries don't like all that kind of stuff, it creates jobs for us, right? So the power electronics people have to come into the picture and make people happy, make the laptop manufacturer happy, as well as make the cell phone manufacturer happy by conditioning the power between the cell phone and the laptop, or conditioning the power, which in this case is a DC to DC conversion. In the case of charging your laptop from the mains, it's an AC to DC conversion, right? So our AC power here is what? 240 volts RMS at 50 hertz. In the US, it's 110 volts RMS at 60 hertz. Why the difference is, I mean, it's a different school of thoughts. I think Saudi Arabia has parts that are 220 volts, I think 50 hertz, and then 220 volts, 60 hertz. They have a mix of different frequencies and different voltages as well. They also have 110 volts in certain areas. So it's we will talk about the effect of frequency on sizing electric machines and generators a little bit, and you will see that the higher the frequency, uh, the smaller these apparatus are. So your transformers become a little bit smaller. Your electric machines become a little bit smaller when you do that. Of course, the lower the voltage, the safer it is. Of course. So it's a safety versus economics versus historical inheritance sort of thing of the system, a mix of things, right? So it's we'll talk briefly about that later. So we talked about a DC to DC conversion type, right, where you're charging your cell phone, an AC to DC conversion type. Sometimes you want to charge. Sometimes you have a wind turbine, right? Wind turbines have generators on them. These generators are producing AC output voltage. Right? They're typically going to be producing AC output voltage, and this AC output voltage depends on its frequency and magnitude would depend on the wind speed. Right? So it's a variable frequency AC, variable magnitude AC that's coming in. Where do you want to send that? You want to send that to people's homes, or you want to send that into the grid, right, to supplement the grid. The grid voltage is what? A fixed voltage, quote unquote fixed, because it's when you study power systems, you know that if you studied the 459 course or the 460 course, you know that the power system voltage is not fixed voltage all the time. There is a variation in the control system behind this whole power system. But for the most part, it's a fixed value of voltage and a pretty fixed value of frequency. So how do you convert from this wind turbine variable voltage, variable frequency into to pump the power into the grid or to feed people's homes? You will have to put a power converter in there, right? So that's and that power converter in this case is taking variable voltage, variable frequency AC, converting it to what? Fixed voltage, fixed frequency, quote unquote, AC as well, right? So that's an AC to AC conversion, right? So there's an AC to AC conversion. There's a DC to DC type conversion. There's what do we call? What else do we talk about? AC to DC. So we talked about AC to DC. We talked about DC to DC, and we talked about AC to AC here. So there are four. There's an AC to DC, and this example was the utility to cell phone, right? And then we talked about the AC to AC conversion, which was what? Like the wind turbine, variable frequency, variable voltage, to a fixed voltage, fixed frequency AC connecting, which is where you connect to the grid or the people's homes. Yeah. And then there's a DC to DC. An example of that is, for example, you're charging your cell phone battery from your laptop, for example. What's left? A DC to AC, right? So that's what's a good example of that? Can somebody think?
In your car, plug in like your TV and the power outlet in your car. Or
If it's directly into the power outlet, no, because
cigarette lighter.
the cigarette lighter
You
is
need transverter.
it's an inverter. Yeah, you need so the inverter that is used to, if you want to plug your TV and you into your cigarette lighter, you also put a box in there, and that's an inverter, and that's a good example of a DC to AC converter, right? So all of these functions are done by what we call, the electronic circuits that do this kind of work is called a converter. Converter. Okay. In the general sense that they're called a converter. Okay. The power electronics people have sort of a special terminology. Like they like to add more words to the dictionary. So, for example, the DC to AC conversions, power electronics people typically call them inverters. Right? DC to DC conversion, they didn't find a great name, so they just call them DC to DC converters. Yeah. So that's the best that they could do. AC to DC converters, they typically call them rectifiers. And you probably studied that a little bit in 325 to some extent, the basic diode rectifier. So that is actually one of the big workhorses of the power electronics industry. So we will spend a lot of time on rectifiers. AC to AC converters, they have different names depending on the different families they come from. Okay, so some of them are called cycloconverters. Some of them are called matrix converters. I think right now the hot word or the nice the hot topic that people are working on in relation to this is something very similar to a matrix converter that they call AC high frequency link inverter. So AC high frequency link inverter. So all of these are different types of AC to AC type converters. So this would be the general four families that we're going to study in the course, and we will cover all four classes of converters in the course, right? But we will not cover, for example, in the AC to AC conversion family of converters. There are lots of converters. I mean, there's a huge amount of different types of converters, different families of converters, different technologies and topologies of converters. They all use different types of devices, different types of controls. They have different types of limitations. We will not study, of course, all of that, right? So we will study, a certain subset of the AC to AC converters, a certain subset of the AC to DC converters, a certain subset of the inverter, a certain subset of DC to DC converters. Just because you cannot do that in a single course, right? So the idea is to give you a flavor of all the four different types of power conversion technologies, and then you can elaborate on that, in a graduate course or in a senior project or whatever, right? So typically a lot of senior projects have focused on different types of converters that we haven't studied, for example, in the class. Dr. Haytham, for example, has done a lot of senior projects on the quasi-Z source inverter. The quasi-Z source inverter, for example, or Z source inverter is a type of DC to AC inverter, for example, right? So we don't study it in class, but for example, you will understand how it functions after you take the class. you should understand how it would function, how a circuit like that would function after taking the class. Like conceptually at least, right? Not in detail, you'd have to read about it. So as I said, we will cover all different types of conversion in the course. The textbook for the course will be the Daniel Hart book. You have, I think, a paperback copy of this. They're the equivalent. I just bought this off of Amazon. I didn't take the one from downstairs from the book guys. There are many different books on power electronics. Ned Mohan's book is a very good reference as well on the material. So these power converters are made of what? They're circuits made of different devices, like you've studied in 214, for example, inductors and capacitors, and then you've used these ideal switches probably in 214, right? And towards the end, when you were doing Laplace and stuff like that, right? You were doing this ideal switch, turn on the switch at t equals 0, write the differential equation, draw the waveform, right? So this is very important actually to as a basis for this course. But now we don't. I mean, we will use this ideal switch, picture or image a lot during the course. But of course, we will have to start using some real devices. Okay, so what is this ideal switch in reality, right? So in 325, again, 325 is not a prerequisite for the course, but if you've taken 325, it's a good. It will add some good background to you, right? So in 325, maybe who's taken 325? Again, you don't have to take it, but it will provide some additional interesting background. Yeah. So in 325, you studied, for example, a MOSFET, and you studied, for example, a BJT device, and you saw how these devices behave in a circuit, right? So you said you were looking at, for example, for a MOSFET. I will just draw an N-channel MOSFET this way for now. And this would be the drain current in a MOSFET. And this would be what? The drain to source voltage. So this is the drain terminal, this is the source terminal, and this is what? 325 is the gate terminal, right? So what were you doing mainly in 325 in relation to this device? What were you studying? What were you studying? You were studying amplifiers. You were trying to make sure that the gate to source voltage has a certain value by sticking around certain values of resistors around the device to make sure that the device operates in a certain fashion, right? And when you operate the device as an amplifier, basically there was this set of curves. There was this set of curves, right? So these were different characteristics. This was the characteristic curves of this MOSFET device. At what? What were these different curves for? Different values of gate voltage. Different values of VGS, gate to source voltage, for example. So at different values of gate to source voltage, there were different relationships between the drain current and drain to source voltage, right? That was basically it. So you have a switch. So people who do not take 20, don't worry about it. Basically, you have a switch, right? This switch in 325, they studied it to operate as an amplifier. What does an amplifier do? A simple amplifier, or a simple sort of a voltage divider is a simple example of an amplifier. Just to make it bring it close to home. Yeah. If you have a voltage divider, an amplifier, you can increase the gain or decrease the gain, right? So let's think of a potential divider as something that will decrease the gain, right? So if I have a resistor here and a resistor here, right? And these two values of resistors are exactly the same, and this is my output voltage, right? This is my output voltage plus minus, and this is a 5 volt DC input, right? So what is the output voltage? 2.5, right? It's the two resistors are exactly equal, so the output voltage here is equal to 2.5. So I've changed the voltage from the input. So this is my input side, and this is my output side. I've put an amplifier in there, a box in there. This box can, increase the signal's value, decrease the signal's value, change its frequency response, do whatever. That was the amplifier, right? You were, and at the end of the day, in that course, you were coming up with transfer functions to define your circuit. So you can make this transfer function look like anything you want. This is a simple transfer function where I'm just dividing the magnitude by 2, right? And you can do that very easily with this circuit, correct? Can somebody tell me how you would do this with a MOSFET for the people that took 325?
You have the voltage source coming in from the D, and then you would have to have some sort of source of power coming into your gate.
Exactly.
That describes how much gain you have.
Exactly. So I can replace this section here. I can replace this section here with this MOSFET. And as Khan said, I need something to add a gate to provide power to my gate. And this provides power to the gate with respect to the source, right? We said that this is different VGS values, right? So this is providing power to the gate with respect to the source. So I'll just draw it this way. It's a voltage source that is sort of providing voltage to the gate with respect to the source, right? I'll draw it this way. How do you build something like that? We can talk about that later. I'll bring you stuff from our lab to show you some examples. Yeah. But basically, this is an equivalent. I can do the equivalent job that this potential divider is doing with this simple circuit, right? Why is that? Because this MOSFET has a characteristic that looks like this. What is this characteristic? This characteristic is the relationship between the voltage and the current. So it's the current through the MOSFET and the voltage across the MOSFET, right? There's a relationship between the voltage through the MOSFET and the current across the MOSFET. And we know that there is a relationship between voltage and current through a device. It's called Ohm's law, right? So what we did by adding this, in this circuit, this was this R, right? If I wanted to drop 2.5 volts across, basically what I did here is I want to drop 2.5 volts across this resistor so that my output voltage is 2.5 volts, right? So what do? I know that there's a relationship between voltage and current across the resistor. So I say V equals IR, and the V I want to drop across this resistor is 2.5 volts, right? And for example, typically you have to know your loads, right? I know that if you were doing some contracting work over the summer for a company, I mean, you're building a power plant for a specific load. You were building a power plant or a distribution system for a specific load. So typically your loads are known. So you typically know that your load is, 1 watt, and it requires 1 volt. You know that, right? So it's easy for you to do, if you know that your power consumption of your load and your voltage rating of your load, you can easily calculate the current, P equals V times I, right? If you know the power consumption of the load and you know the voltage rating of the load, this is something you have to know. Loads are things that you need to know, right? When you ride, electric car, they build, put a big motor and a battery, right? They know the car's weight, they understand aerodynamics, they understand road tire interaction, and based on that, they've designed their electrical system. So it's the same thing here. Because you know the power rating of your load that you want to feed, you know the voltage rating of the load that you want to feed, then you can calculate the current. If I know the current that's flowing in here, right, I can substitute that in this. Let's say it's 1 amp, right? And then I can calculate the corresponding resistance, right? So I was able to calculate the resistance that I need to stick in there. And you can do the same thing with a MOSFET, but in a controlled fashion. Here, if I want to change this 2.5 volts, what do? I have to change this resistor, right? My load is not going to change, right? My load does not change. So what I would have to do is I would have had to change this resistor, right? Which is, you can do it. You can add a potentiometer. You've studied that in 214, right? a simple potentiometer, you can change the resistor, and it will change the output voltage here from 2.5 volts to whatever you want. Of course, based on the equation, the relationship between V and I and R. In a MOSFET, it's nicer because you can do that in a much better way, and you can do that in a lossless, no, not lossless fashion now. No. We'll talk about this lossless fashion later. But you can do that in a controlled fashion with a MOSFET as well. So if you provide different gate-to-source voltages, your operating points, so if let's say you're pushing a current of 1 amp, then there's a specific operating current here, right? If your drain current needs to be 1 amp, right? Then you have a specific current that you're operating at, right? So these curves here will intersect this 1 amp, for example, value of drain current at several points, can intersect here, can intersect here, can intersect here, maybe another one will intersect here, or whatever, right? So there will be several operating points that you can operate at, right? And they will be based on different gate-to-source voltages, right? So if you provide a different gate-to-source voltage, then you can rely on these different operating characteristics. That's fine. So what is the relationship between V and I? So this V and I, it's basically what's happening across the MOSFET, right? This MOSFET has ID flowing through it, which is 1 amp, and different VDs across it. This is the VDS across the MOSFET, different voltages across it, depending on the gate-to-source voltage that you've applied, right? So depending on what gate-to-source voltage that you've applied, I can have different voltage drops across the MOSFET. Different voltage drops across the MOSFET is equivalent to what? Different voltage drops across this resistor, right? So I've done the same thing, right? So I've done the same thing with a MOSFET in a controlled fashion, electronically. Like now I can, instead of having somebody to sit down with a potentiometer, right, across and change this resistor value, I can, maybe program that in a microcomputer to change the value of the drain to source voltage, for example, somehow. Like maybe there may be a circuit along that needs to take care of that as well, yeah. But you can do that with a MOSFET. So what did I do? I made the MOSFET look like a variable resistance, right? And this is what the 325 people studied. We don't do that in power electronics, right? That is fine. I mean, this is what, and you can do that. And this is called the linear power supply. Linear power supply. This is a basic example of a linear power supply. Why? Because you've basically operated the device in its linear zone. This is called the linear zone of a device. That's what you studied in 325. You would always be operating in the linear zone, right? What's the disadvantage? Again, I'm sorry for the people who didn't take 325. Don't worry. Again, this is just I'm trying to show them that what they took in 325 is not very useful for us. That's all. That's all I'm trying to show. I'm just kidding. It's useful, but so why is this? What's the disadvantage of doing it? Here, it's great. You can control the voltage. You can control the voltage very precisely, actually, across this device, and you will get what you want. You put in 5, you get 2.5, you get whatever you want. So you can do the job. Sure, you can do the job. What's the disadvantage of this circuit or this circuit? What's not the disadvantage. What sort of a limitation or a consideration, a design consideration? How would you choose this resistor, for example? Forget about this for a while. How would you choose this resistor? What's when you choose something, when you're choosing equipment in a power plant, right? You're choosing it based on voltage rating and current rating, right? Voltage and current rating corresponds to a power rating automatically, right? So when you choose a device, fine, I chose the value of resistor R. If I tell you build this circuit, you will choose the value of R. That's no problem. You can do that because of the math, right? But if you come to build it and you use a quarter-watt resistor, these small, tiny, flimsy quarter-watt resistor, it may burn, right? Because if I have a current in there of 1 amp and this resistor is 1 ohm, right? Then I squared R is what? 1 watt, right? So if you use these flimsy quarter-watt resistors, what's going to happen to it? It will burn away, right? So there's a lot of power loss associated with this circuit. It does the job, but there's a power loss associated with it. How about this type of circuit?
They short out really easily.
Same thing, right? Because it's the same thing. What are you doing? You're still you're dropping a voltage across a device. If you drop a voltage across the device and then there's current flowing through it, what do I have burning through? Power. I mean, it's voltage across and current flowing through. P equals V times I. So I'm burning power through the device. So I'm burning the same amount of power through this MOSFET as I am burning through this resistor, which is fine. If you're okay with that, if you have a lot of extra power and you don't want to worry, you're not worried about efficiency, it's okay, right? But if you are concerned about, for example, building a power supply that you're going to be putting out in the desert, right? The ambient temperature, 50 degrees C. Ambient temperature, 50 degrees C, and then with power losses, what are you doing? Generating more heat, right? If you're generating more heat, it means the temperature will rise above ambient, right? So it's very, I mean, we'll talk more about temperature and power losses later, but it's very important for you to, when you're defining, looking at thermal considerations. So power electronics people have to understand a lot about the mechanical aspects of things, right? So you will be expected to understand the thermal considerations when you're working with mechanical guys. You're building a power electronic device to, you're building a power electronic device to power up this laptop, right? Apple wants to make this as cool and as small as possible, right? As light and as cool and as small as possible, right? And they're willing to, pay an extra few cents and us pay a few extra $100 for that purpose. But at the same time, maybe you go buy a big Dell power supply, right? I mean, they were probably bigger, bulkier, etc., etc. They're doing the same job, right? But they decided that maybe form factor is not a big consideration. Versus Apple decided form factor is my number one consideration, right? So designing a circuit for this, even though I'm doing the same thing, I'm converting 240 volts to 15 volts. Same exact spec, at least voltage input, voltage output spec. But there's other parts of the spec that are not the same. Size is not the same. Efficiency is not the same. Can I make something that is very small and so condensed and I make it inefficient? If I do that, then the heat will sort of eat up everything around it, right? So definitely the efficiency consideration, if you have something put in a tighter space versus something that has a big space to operate in, right? If you have a big area or big surface, for example, the heat will dissipate, right? So you can live with a lower efficiency there. But if you have a very small space, limited, confined, it's going to be sitting on somebody's lap, for example, or something that's going to go in an oil and gas application where you're sending it in a well where the temperatures are 150 degrees C plus, up to 200, 250 degrees Celsius, then you cannot do that, right? So you will be designing, for a similar input-output voltage spec, but the rest of the considerations are very different, right? So we will talk about how to work around that. But for example, in this case, this linear power supply would not be a great choice, right? It's dissipating a lot of heat. So people typically use linear power supplies in places where, for example, you cannot tolerate any noise, electrical noise. Meaning what? Electrical noise. Okay. Yeah, so I was going to draw that right now. I just don't want to erase something, but I will erase. So all of this was, what we've been talking about is how the 325 people approached business, or the way they approached this function of converting voltages to each other, right? The power electronics people use almost exactly the same circuits as this, almost. Let's think of it very similar for now, but let's use an ideal switch for now, and do this. And let me redraw this operating characteristics again, but smaller. These are the device's operating characteristics. This is just from the datasheet of the device, right? What the power electronics people do is never operate here. Never operate in the linear region. When you operate in the linear region, what are you doing? You're making this MOSFET look like a variable resistance, right? That's what we concluded. Same function as a variable resistance. But what the power electronics people do is they operate here or here. They only operate in what's called the saturation zone here, or the cutoff zone. So what's happening in the saturation and the cutoff zones? When the device is on, I have drain current flowing through it, right? And I have, I mean, this is the ideally, okay, this is the real characteristic of the device, right? This is this line here, and these curves. So let me, this is wrong for now. This point is wrong for now. I'll get back to it later. So if I want to push a certain amount of current, certain amount of drain current, then I'm gonna be here, right? I will be operating on this line. And the amount of voltage across the device will be this, right? Is it a large voltage or is it a small voltage compared to operating, for example, here? A much smaller voltage, right? It's a much smaller voltage compared to operating anywhere in the linear region, right? So if I have a high current and a much smaller voltage, then I can do what? Then the power losses across this device have been decreased considerably, right? So the amount of losses through the circuit have decreased a lot. But I'm not doing the same amplifier thing anymore, right? I have to think in a different way, right? The way power electronics, okay, and then when the device is off, what am I doing? I'm operating here. I'm blocking the voltage. I'm blocking a certain amount of voltage, and there's no current flowing through the device at all. This looks like what? This looks like the ideal switch, right? What does the ideal switch do? Ideal switch, when it's open, it's blocking. What's the voltage across this switch? This is VDC. What's the voltage across this switch when it's open? No, when it's open.
VDC.
Yeah, so it's blocking the VDC voltage, right? So it's blocking the full voltage. And that's what's happening here. I'm able to, I mean, if I make it look like an ideal switch, I'm able to make it block voltages, right? And when it's on, what's happening? For the ideal switch, when it's on, I have current flowing through. And if you think of this, an ideal switch, if it's a pure ideal switch, then you have current going through, and then there's 0 voltage across it, right? But think of this ideal switch as something that has a small resistance as well. If you think of this ideal switch as something that has a fixed small resistance, then the power drop across it, when there's current flowing through, is a small value. The small value can have high currents. I can push the whole ID current that I want to push through. But because the value of resistance is small, then I have a small voltage drop. Then the power losses are very small across this device. Right? So if I'm able to operate in this fashion, right? This is big ifs right now, right? So if I'm able to do this, then I can satisfy my wants, my need to convert the voltages as well as minimize losses. But let's see how that happens here. So let's look at this value of R. Where does this value of R come from? In this type of relationship, in a real device, we said we're going to operate along this line, right? So I'm never going to operate at these extensions of the characteristic curves of the device. I will operate across this line only, right? So if I operate across this line, I have a relationship between current and voltage across the device. At every value of current, I have a relationship between current and voltage. Every value of current, I have a relationship between current and voltage. Here, I had the same thing, right? But I had many. At every value of current, I had several relationships between current and voltage. So in that case, I had V equals I. My relationship is V is equal IR. So I had the relationship between voltages and current. So I had a single value of current, for example, and many different values of voltage that this can correspond to. Meaning I had what? Did I have a single value of resistance? No, we had a variable resistance. That's how we did this funky transfer, right? That's how we did this control over the output voltage. We made this look like a variable resistance, right? So we had many values of resistance for the device. Here, in power electronics, I don't do that. I don't operate here at all, where I end up having many values of resistance for the device. I only operate, let's say, along this line. When the device is on, I operate along this line. If I operate along this line only, then the relationship between voltage and current is what? It's linear, right? It's a linear relationship. So it will always be the same value of resistance, right? So if you decrease current, voltage will decrease. What does that mean? If this decreases and this decreases, then this can stay constant, right? So, and that's what happens. The relationship between them is such that the slope here is always fixed. And this slope is actually the resistance of the MOSFET. You probably heard the RDS on, right? The drain to source resistance, right? So that's something you study in 325. You don't need to know the history, but the RDS on is just basically this resistance of this switch. So now I'm only utilizing RDS on across the switch, which is a very small value. Because again, RDS on is a slope of the relationship between the voltage and the current. So if this is the relationship, then RDS on is very big. And that's not what's happening. Typically the characteristics are such that this slope is very small. If you dig out any MOSFET characteristic curves, and we will look at data sheets, then this curve is this line is almost vertical actually. So almost vertical. So actually, ideally, sort of, we say, okay, this line is vertical. We don't even have a slope. It's so small, then we just assume that the MOSFET operating characteristics looks like this. This is ID, and this is VDS. And when the device is on, we have current through the device and 0 volts across it, typically, almost. And when the device is off, we're blocking the full voltage, and we have no current at all through the device. Of course, both are science fiction, right? Because in real life, when you have voltage across a device, any device, if I have voltage across any conducting, material, right? Anything, then there will be some leakage anyway, right? Even across a capacitor, right? The capacitor is supposed to, two plates with a dielectric material. This dielectric material has a leakage component to it. And this leakage may change with temperature, may change with the value of voltage, etc. But it's a leakage current, right? So we will forget it for now. We will not be interested in it for now in our course. But for example, if you're designing a power supply, for example, like we used to do for operating in an oil and gas environment that is operating at 150 degrees Celsius, the leakage characteristics of devices are very different at 150 degree or 200 degrees Celsius. There's a lot of leakage. So in that case, and we're always operating the devices out of their area of comfort. Right? It's like taking this class outside in the desert, right? This is not your area of comfort. We will not be happy. The devices are not happy in a downhole application, right? It's very hot outside. They don't like it. The devices, if you look at data sheets will be rated for what? For, up to 125 military applications. Now people, because of the automotive buzz, people are pushing 150. If you're pushing the limit, you're 175. You'll find a data sheet for a device that's operating up to 175 degrees C. But at 175 degrees C, we'll look at these characteristics and we'll see that they are recommending that you draw 0 power through the device at 175 degrees C. Right? So what do you do in a downhole application where your ambient is 175? You have to derate and test all the devices and worry about leakage current and worry about these extra things that you would not worry about typically in an application like, a computer power supply. Or a desktop power supply, which is even, okay, I have enough space, I don't care, blah, blah, blah. So it's very different. I mean, even though the voltage input and output are the same, the design, the way you design it is different. The frequencies are different, the components are different, etc., etc. So fine, we sort of moved away from what people did in 325. We said why it's not good. Why is it not good again? Why is it? What's the limitation? Not good is a bad word, but the power loss is a drawback. Let's say is a drawback. Is a drawback that we would like to consider. But it does the job, right? The problem with what the power electronics people do is something else, right? So we've solved the power loss thing. Does everybody get the idea of, okay, this was the original characteristics, and now really a MOSFET, if you operate it only in saturation and cutoff, looks like this. It looks like the ideal device, ideal switch. So forget about 325. We're operating a device. We're operating an ideal switch, except we're adding a little bit of a twist. Instead of just an ideal switch, we're adding a switch with a resistance through it. That's all we're doing. Okay, that's all we're doing in 438. And this value of resistance, I sort of, I can give you this value of resistance and tell you it's a small value. I'm just trying to relate it to what you studied in 325 for those who've taken 325. If you have not taken 325, yes, it's a very small value of resistance that you can calculate from basically the slope between the relationship of voltage and current. And the slopes will be very, very small. So what we did was we approximated, we came close to this ideal switch sort of image, or whatever you want to call it, characteristic that we have used before in 214 and studied, etc., etc. But if I do that, can I take this VDC, can I take 5 volts here and produce 2.5 volts? What's the mechanism? How can I do this then? How can I still want to do the same job, right? I'm trying to do the same job with 3 different circuits, right? This is a simple voltage divider circuit. Everybody's okay with that. This, people who are more comfortable with 325 are very okay with that. Hopefully others sort of get an idea. You're operating the device as a variable resistor, and there's a way to control it based on the characteristics. Both of them have the same issue with losses. This needs human control. This can be computer control. Right? That's the main difference. Or this can have a small control loop, analog control loop doing it, for example. Then the third type of circuit that we want to work on is the power electronic circuit. So this is what our course will be discussing, is something like this. If I want to do the same job, convert 5 volts to 2.5 volts with my kind of circuit, with the power electronics type circuit, how do I do that? Can I just keep the switch on like I kept like the MOSFET here? What would you do? Let's forget about power electronics. Just you have an ideal switch. Can you produce 2.5 volts DC from your ideal switch circuit? You have a voltage source here, ideal switch, and you want 2.5 volts at the output. This is what you want. How would you do that? How would you approach that? But if you add any sort of impedance, then you're going to have power loss. Right? Impedance, current going through it, power loss. Then we go back to the linear power supply, which we don't like. That's 325 materials, old stuff. Old school stuff. You don't have typically you don't have control over your input and output, right? When you're building a power plant, the utility is giving you 132 kilovolts. Convert that to 11 kilovolts. You don't have a choice. Input and output voltage will be typically dictated. Your load, same thing. I have a laptop that needs 15 volts. This is 240 volts. I cannot control it. I have to build something in the middle that does this conversion in a efficient manner. So one way to do it, how about use the idea of averaging, right? If I have 5 volts coming in here and I close the switch for a while, this is 5 volts, yeah? This is time. If I close the switch for a while, what voltage do I see at the output? 5. So I will see 5 volts at the output. How about if I open the switch? What volt do I see? 0, right? If I do this, and this is T on, and this is T off. And I keep T on and T off exactly the same. Right? Then what's the average value of voltage across the load? Right? So if I do that, sorry, my drawing is, I'm not a very good drawing to scale kind of guy, but the average value of voltage in this case across the load will be 2.5 volts. So that's the average value of the output. But of course, that's not I'm not doing the same thing anymore, right? Here I'm delivering a nice, smooth 2.5 volts to these loads. Versus here, what am I doing? I'm giving this load something, it looks like this, like a pulsed waveform of 5 volt 0, 5 volt 0, 5 volt 0. It's not equivalent, right? But what do you think you can add something that will sort of change this sort of waveform to this? A filter, right? And that's exactly what we would add here, some sort of filtering stage. If you add a filtering stage here, I don't know, maybe a capacitor here, and maybe an inductor as well sometimes. Maybe. There's not necessarily, okay? So we'll study this filter stage in detail later. But basically a filter stage. Here I'll just put an L and a C just for the sake of, generalization. But if I add a filter stage between my, this pulsed waveform here, over at this, between these 2 points, what do I see? I see this nice pulsed waveform. It has an average value. I know the average value of a pulsed waveform. If I have T on, T off equal to each other, I know that if this is 5 volts, and the average value of it is 2.5 volts. I know that. You can do the Fourier series, or you can find the average value using the, 1 over the period integration of the waveform, x of t over the full period. You will get 2.5 volts. If you do that, and you add this filtering stage, assuming you're able to design a proper filtering stage, right? Then what do you get at the output? You get this nice smooth waveform. Is it going to be as nice and as smooth as what you get here? No, because any filtering stage will have a cutoff point where you will still have some AC component, because again this is a pulsed waveform. This part of the waveform, what sort of frequency content do these edges have? When you're studying 314, I think you're studying the sigma, like the sigma function, right? There's what is it called? Impulse function. Impulse function. What sort of frequency content is in the impulse function? Three fourteen. I'll tell Dr. Karaki. Who is Okay, forget about what you studied, but okay, if you have something that changes very fast, okay, let's say if you have something that doesn't change at all, it will have just a DC content. If you have something that, I'm trying to relate physical concepts to math, right? If you have something that is DC content, but you have small changes to it, that is slow changes to it, slow and periodic change to it, it will have the majority of this signal will be a DC content, right? And a small amount of it will be that, frequency that is changing, that is overlaid on top of that DC content. The DC content will be, if you do the Fourier series, the DC content will be way up there, and then this AC content, if it's a low frequency AC, it will be here. If it's a higher frequency AC content, maybe it's here, right? If you do the FFT, right, so on the power spectral density curve, so and that's the same way in power electronics, right? So if these are like the impulse functions, right? So I have some DC value here, and then this is impulse. This has a lot of frequency content, right? So if these square waves, or these square waves, because of this sudden change that they have here, have a lot of frequency content into them. They have a lot of frequency content, and you can filter. You can add a low-pass filter, of course, right? If you draw a characteristic of a filter, the gain plot of a filter, for example, looks like something like this, for example, right? This would be the gain in dB, right? And this would be what? Frequency, right? So at low frequencies, you should, you will have, maybe, for example, you will design it for unity gain, right? So whatever you put in, you will take out. And then, so that means that if I have a DC content, like the average value is what? What's the average value of a signal? Remember when you were doing Fourier series, you had a periodic signal, and this periodic signal, you were taking it and you were coming up with 3 equations, right? The average value equation, ANs and the BNs, right? Or the ANs and BNs, you're combining it into a CN, which was the harmonic component of the Fourier series of that waveform, right? So you had an average value, which is what? It's actually the DC component. That average value of the signal is the DC component in that signal. The whole DC component signal is represented in the average value of the signal. So if you have a signal x of t, the average value is 1 over the period integration of the signal over the period, right? And then the ANs and the BNs were multiplied by sine and cosine functions. These ANs and BNs were all the AC components in the signal. So any signal that is nothing but a pure, nice, smooth DC will have some AC component. So any signal that is not very smooth will have a DC component and an AC component. The AC components are all these ANs and BNs or CNs multiplied by sines and cosines in the Fourier series. and then the DC component is the average value. So if I'm able to design a low-pass filter that will allow, it's a good gain for the average value. At low frequencies, it passes the signal. It passes the average value through, right? So my DC signal will go through nicely. And then what happens to my higher frequency components? They are attenuated. Do they suddenly disappear? They're attenuated depending on the design of the filter, right? You've studied, for example, single-stage filters, or single-order filters, second-order filters, third-order filters, fourth-order filters. The higher I increase my order of the filter, what happens to this drop-off curve? I can make it look like this, maybe make it look like this, maybe make it look like this. So I can make the higher frequencies disappear quicker, right? But am I eliminating them? No. So there's always something called ripple in a power supply. In a power electronics type power supply, so even though I've designed my filter stage, I've done a decent job designing my filter stage, but I will always have some sort of ripple. And this ripple is also a spec of a power electronics power supply. So you will typically be given power supply design, but not just, okay, I want a certain input voltage and a certain output voltage. No, not just that. I will tell you I want a certain input voltage and a certain output voltage. I also want a certain ripple spec. That ripple spec will automatically tell you, okay, this is the way I design my filter, right? Because based on the way I design my filter, this ripple content will change, right? So hopefully, I wanted to give you the reason why. This is where when we talk about ripple, we're going to be talking about designing this filter, how we design this filter. Amount of ripple in a power supply output depends on the load. For example, if you are just merely operating a heater, a resistive heater, for example, you just want to heat the room, and you want to put power through this heater, right? And this heater operates on, I don't know, if you want 10 volts DC, for example, into this heater. Do you really care how much ripple content is in this application? I don't really care at all. I really don't care. But if you are, for example, doing 3D printing, if you are building the latest and greatest 3D printer that is micro-positioning the extrusion process at, 16 microns, resolution, right? The extrusion process is driven by a heater. And the extrusion process positioning is driven by a motor. This heater and this motor are supposed to operate with the resolutions that are so high. If I'm not going to be delivering precise power to the motor and precise power to the extruder, right, then I will not be able to meet this 16 micron resolution. I can build a 3D printer, no problem. I can build a power supply for a 3D printer, but the resolution will be higher. The extrusion process will not be as precise because I'm not controlling the heat into this device or the position precisely, because an application like that would require a very precise knowledge of voltage and current and control of the device's actuating characteristics. So I want to put exactly this much torque to position the device exactly at 16.5 microns instead of 32.5 micron, right? And we're talking about very small distances here, right? So ripple is important depending on the application. So ripple content, there are many applications that you care, many applications where you don't care, right? So why would you pay for a very big hefty filter, right? Why would you pay for a third or fourth order filter in an application where you don't need a third or fourth order filter, right? You won't, right? So, and then, so this is sort of the filter thing. So another consideration that's interesting as well is so this before we go move on. So this is, I said, this is T on, and this is T off. T on, T off. So the time that this switch stays on versus the time that the switch stays off is a critical time in power electronics. We give it a name. We call that duty cycle. So this is also an important consideration. So it's called duty cycle. So it's the time that the switch spends on. It's called duty cycle. So that's the switch's on time duty cycle. Or you can calculate the switch's off time duty cycle. So it's the time that the switch stays on or off depending on what I'm asking for. If I ask for the switch's on time duty cycle, it's this T on. If I ask switch's off time duty cycle, it's the T off. So it's duty cycle is sort of a portion of the full cycle time. So the full cycle time is called period. That's a switching period. And we typically give it a TS sort of variable. We use a variable TS. So there's a switching period. Within this switching period, the device is on for a certain time or off for a certain time, right? It's complementary, right? And the sum of the time on plus the time off is what? Is what? Is TS, right? So the sum of the T on plus T off is TS, right? So the sum of this, this is TS here. So this is TS, this is the switching period. And the sum of T on and T off is equal to TS, right? Always. So, and the duty ratio is typically given as a percentage. So typically the duty ratio is given as a percentage equal to, let's say, T on over TS, or T off over TS, if I'm looking at off time duty cycle, right? So is this going to ever be greater than 1? Never, right? So T on and T off will always be less than 1. So the duty ratio or duty cycle is typically given as a ratio or as a percentage. So I can tell you the duty cycle is 0.1, or which is 10%, or it's 0.5, which is 50%. So it's typically given as a percentage or a fraction or a tenth, a fraction of a 10, right? Or a fraction of a 1. So that's typically how we give it, yeah. So let's talk about something else that's interesting, and then we will wrap up. So we talked about what's the inverse of TS? What's 1 over TS? Yeah, 1 over the period is frequency, right? So, and we typically call that switching frequency. So Fs we call switching frequency. Fs we call switching frequency. Okay, and then how fast do we want this? Do we want the switching frequency to be very high, or do we want the switching frequency to be very low? Why? There's a good answer. I mean, there's a good reason to make it this way, and then there's a good reason to make it this way. It depends on your application. It will be very application dependent. So we will see later in the next class that, for example, in very, very high power applications, the devices themselves have a limitation on switching speed. So you don't have a choice. That's one reason to go low, right? Another reason to go low is that every time you are switching, right, what's going on? Actually, what's going to be happening is the current will go down. I mean, this is current, right? I said this is current, or this is current with time. For example, if this is current, ID is going through this switch, right? I have current ID through the switch. When the device is on, I have ID going through. When the device is off, what do I have? 0, right? So current is going through and then 0. Going through, then 0. What's happening to voltage? What's happening to the voltage across the device? But is it in sync with the current or out of sync with the current? Out of phase with the current, right? So if the current is, when the device is on, there's current going through the device. right? And then the device is off, there is zero current, theoretically speaking, right? And then on, off, right? And then voltage is doing exactly the opposite, because when the device is off, we said what? That this voltage across the device, there is no current flowing anymore, right? So if there's no current flowing, then there's no voltage drop across this load. Then this voltage, the supply voltage, is blocked by the switch, right? So the switch is seeing the full voltage, right? So it's exactly the opposite. The VDS is exactly the opposite of the current, right? And then here I drew them very ideally, but if you look closely what's happening here, is there such a thing as an infinitely fast switch? No, everything has time. There's a rise time and a fall time, and we will look into data sheets and we will look and calculate these rise times and fall times and see their effect on something I will talk about now. What happens if there's if current falls slowly and voltage rises a bit slower as well, what's going to happen during this transition zone? Initially I was saying current will fall right away, and then voltage will rise right away, right? So what was happening during the transition zone? They were not seeing each other at all, right? I was coming in, all the students were coming out of the class. We don't have class, everything's nice, right? So there's no loss, there's no waste of time taking the class. But if they see each other, no, not really, I mean, this was a bad joke, but this was, and really it's what's happening is if current and voltage happen to, they will see each other because current will fall slowly and voltage will start rising. So there will be a period where they're overlapping. So there will be voltage across the device, and then there will be current through the device as well, which means that there is power loss, right? So if I am switching fast, right, then I'm increasing my switching losses. So there are different types of losses in power electronics, right? So losses are divided into conduction losses and then switching losses. So it's time, we'll stop here now, but I think we've tackled the low frequency one. The next class, the low frequency means if I do this, if I switch at a lower frequency, then this happens less frequently, right? So it happens less frequently, so I have less switching losses, right? So I have two reasons for switching at low frequency, right? The limitation of the device itself, and then maybe decreasing my switching losses. These are two interesting reasons. What happens to the filter when you're switching at low frequency is something we will discuss next time, and the benefit of going to high frequency we'll discuss next time as well. So we'll stop here and we'll see you on Wednesday. I did not go through the full